forward to the cloud. All right, so thanks again, everyone, for tuning in on a different week than usual this month. So our presenter today is Dr. Apurva Oza, who I think some of you already know, but Oza did his PhD in France at the University of Sorbonne, and he then spent some time at the University of Bern and is now back in the US and about to start a new position at JPL. And he is going to talk to, and so Oza has worked on exospheres across the solar system and beyond. So from the icy satellites to exomoons. And, you know, of course, there's the fundamental processes operating in all of those situations are very similar to those at the moon and Mercury. And of course, I know several of us here are also interested in the icy satellites themselves. And so, so Oza is going to be sharing with us today some of his work on sodium and oxygen outgassing on Io Europa and beyond the solar system. So I will hand it over to Oza to introduce himself a bit more, if you would so like, and then we can all sit back and hear about what he's been up to research-wise. And so, just before I hand it over to Oza, just a reminder to everyone: unless you're speaking, please mute your microphones. Cameras, feel free to have them on or off, whichever you're comfortable with. And Oza, would you prefer if we interrupt you with questions, or would you prefer if we wait until the end?
Oh, yeah, please interrupt me. Make sure I don't talk too fast. And yeah, I'm happy to hear questions. Yeah.
Bye. All right, awesome. So I will hand it over to you and put myself on mute.
All right. Thanks a lot, Parvati, for inviting me to this Friends of Lunar Volatiles group. It's my first time, so I see a lot of familiar names and faces virtually, so that's really cool. And I hope everyone's doing well at home or in office, wherever you guys are. But yeah, I guess I haven't seen or given this talk in at like DPS or anything recently. So hopefully it's somewhat new to some of you that are aware of the sort of extrasolar IO work that we've been pursuing, and then also advances at Europa. And I thought I'd focus on those two bodies in terms of volatiles. And I was sure to include lunar volatile in the title so that it's appealing to all audiences here. Okay, so just starting with the bulk term outgassing. Outgassing to a near surface atmosphere can be a conglomerate of various processes, not just sublimation, but also evaporation, desorption, venting, and then of course cryovolcanism, which is for now, at least in my work, just beginning to occur at Jupiter's moon Europa because of the observations that we'll discuss. And then this also might be the origin of Earth's atmosphere. And I've only mentioned this because I've gotten into some work with early Mercury, the magma ocean of Mercury's earliest atmosphere. But that's something I may only briefly touch on. And then, of course, there's outgassing to an exosphere, meaning this is more or less mass loss, but just using it as a bulk term. This can include magnetospheric ion sputtering, which can result in atmospheric sputtering, which results in loss to space, which is what we think occurs at Io. Then, of course, there's solar wind implantation that can occur at the lunar exosphere, as well as incoming X-ray and extreme ultraviolet radiation, which is known to result in very high mass loss rates at exoplanets and may even shape the actual population of exoplanets. That's something I worked on extensively in Bern in terms of evolving sub-Neptunes into super-Earths. So we know that outgassing can be a fundamental planetary evolution process. Right, so as I said, I'll try to go over Europa and Io, and it's particularly ExoIOs. And the volatiles that I'm mainly focused on is just oxygen and water at Europa, and then the alkali, sodium and potassium, as well as sulfur dioxide at Io. And so I'll be focusing on sodium and then oxygen for both bodies. So starting on ocean world, something a little bit closer to home before we go out too far, Europa. So many of you may be aware of this history, but if not, the origin of molecular oxygen was predicted well in advance in the 1980s based on the Voyager measurements, which was very exciting to many people. And the Voyager measurements actually enabled an estimate for the column density at these bodies, at Europa, Ganymede, and Callisto, namely by Bob Johnson, who is probably a very good friend of lunar volatiles in general. But that was actually very fascinating, that there's this link between the plasma and then exogenic flux coming in and a source of an atmosphere. This is due to radiolysis, that when you get this radiation or these ions, can actually break up the ice into H2 and O2, and then desorb significant quantities of O2. And after that, in 95, it was found that O2 bubbles can actually be found inside the icy satellite regoliths. Although so far, the dimer absorption feature hasn't been reproduced by radiolysis. And so it's still a mystery in terms of how exactly one can trap the O2 inside, but it seems to be probably due to something such as balancing the thermal diffusion as well as the mass loss due to the ion bombardment as well as desorption. So that's some work in progress, but just continuing on into the atmosphere. Now we've got something, we're building the surface regolith, and now that surface regolith is going out into an atmosphere. And so as we know at Europa and Ganymede, the prediction was confirmed to yield approximately the same number of molecules per centimeter squared as was predicted in the 80s. But just note that this isn't any direct detection of O2, this is atomic oxygen aurora. So excited oxygen that are then subsequently photoionized and electron impact associated. And so essentially at Europa, we think that there might be three principal reservoirs of varying magnitudes. First of all, there's the regolith that exists in the near surface that may also include damaged grains, and then also trapped O2. This is the stably trapped O2 that is seen in the dimer observations by John Spencer et al. And Wendy Calvin. Atmospheric O2 then is the previous observation. And so there's different constraints of oxygen at these bodies. Generalizing, of course, for Ganymede and Callisto, which aren't identical to Europa, but Ganymede appears to be similar, although there's the additional problem of the magnetic field. So in 2016, though, there was evidence of diurnal evolution, which ultimately led us to believe that unlike the original prediction of the column that was due to direct magnetospheric ion sputtering, the O2 may be thermally desorbed due to heating within the regolith, and then the O2 just fumes out. And the precise binding energy was also constrained in a paper we wrote in Space Science Reviews, where the value of 0.14 electron volts, which is actually higher than the direct sputtering value of 0.06 electron volts. But this plot right here just shows the dusk over dawn ratio along with the sub-observer longitude. So you can see as Europa goes around its orbit, it reveals different, let's say, different times of the day to the observer. And of course, the side right here at 0, the high error bars are due to it entering eclipse, the difficulty of the observation, I'm sure. And so every point, with the exception of these bizarre eclipse points, occur predominantly at the dusk side versus the dawn side. So there appears to be a bulge of O2 at Europa. And bulges will be a big theme for this talk, if not oxygen bulges, but sodium bulges or clouds. Yeah, so other than that, it's interesting that the trapped O2 may be the overwhelming majority at Europa. That's just one thing to highlight about this new phenomena. Right here, it's very small, I know, but it's just very quick to show that radiolysis occurs, and then after radiolysis, there's thermal desorption that releases into the atmosphere, and then that O2 continues to be heated, continues to be trapped, and may actually vent down into the ocean. So this is a submitted paper led by UT Austin professor Mark Hesse. We worked with him and his PhD student on figuring out how the O2 that we can constrain from observations from Hubble Space Telescope and also other constraints, that quantity of O2 that lives in the reservoir in the regolith of Europa, how does that O2 then funnel down to the ocean? And this is due to a brine percolation mechanism. That's actually the salts that take it down. So that's actually very exciting work. That's the latest work I've done on Europa so far. But very exciting to think about because, of course, I think this O2 feeds the fishes down there. So yeah, but continuing to more, let's see, more exospheric work. This is an old plot from 2018. And since lunar volatiles, I was thinking of the moon, which I actually haven't worked exclusively on ever, but right now, the model that I did develop for the tidally locked satellites can actually constrain where the bulge may be or where bulges may be on the moon, such as the argon bulge and the neon bulge, which don't actually peak at noon local time or at night local time, because at midnight local time. Because as Hodges and Johnson showed, these volatiles actually evolve with the thermal gradient. And so that's very, very similar to the formulation we came up with to produce this dusk over dawn symmetry ratio. I'll go into that in more detail now. Okay, so O2 addition. Yeah, so this equation right here is just a 1D mass conservation equation that follows the column density over time. So if we just represent the column density at localized column density, latitudinally averaged, and evolve it, one can constrain this for Europa. So the thermally desorbed flux, we have constraints on based on the dusk over dawn asymmetry, as discussed, and then the loss rate of O2 can be constrained by either electron impact association or charge exchange. And so following the column over time, just in a very toy model scenario, you build a bulge of O2 that eventually lands at dawn. When you solve this equation, you get an integral that is a function of the mass loss rate and also a function of the desorption flux, well, based on your initial value, your initial choice of what is the desorption column. All right, and so after that, after integrating, one finds that there's a fundamental atmospheric evolution parameter. And I think this is, this might be the most, let's see, useful part of that paper in terms of it's very easy to approximate the evolution of a surface bounded exosphere if it behaves in a certain way. So meaning if the atmospheric lifetime is balanced with the orbital period of the volatile and of the satellite, then one can actually predict dusk over dawn asymmetry and actually predict where this outgas cloud or the net steady state column, where it would be shifted from noon local time, if it's thermally desorbed, of course. And we tested this for various models also, including magnetospheric ion sputtering. So that one is also following the leading and trailing hemispheres as well. But for now, I'm just showing how a thermally desorbed source works, so that noon local time is fixed and one can follow that evolution a little easier. So yeah, at Europa, it was predicted to be about 81 degrees. So of course it might be a little less or more, but that is outstanding question until an in-situ spacecraft comes by. Right, so yeah, summary on the O2 slides that I just showed. Say Europa Clipper and the Europa imaging system. All of these instruments will hopefully be able to constrain the column densities and see the nature of Europa's O2. But more exciting stuff or more explosive stuff in terms of the cryomagma that might be inside Europa that results in these plumes that we have evidence of HST, that work is still in progress. In particular, working with Francois Leblanc, who's using a 3D exosphere model. We call it an exosphere general model, unlike a general circulation model that's able to track ballistic particles, and also if they collide, do a DSMC simulation of these particles, and couple that just now couple that with cryomagma ascent models. So there's several predictions that can be tested there, and of course hopefully if the internal let's say the magma timing models can be improved with tidal heating, then that would be very useful in terms of where one thinks that the peak emission should occur due to internal tides, etc. And then finally, a thermal outgassing mechanism was identified, as I had mentioned, in terms of versus the direct ion sputtering occurring. Thermal outgassing is a completely different mechanism where it's fundamentally sourced by radiolysis, which is due to magnetospheric ion sputtering. You can populate the O2 in the regolith, but then the thermal outgassing is what desorbs that O2. And so that's what makes it different. And if people are aware of the Hodges and Johnson Lunar paper from back in the day, this predicted how night side cold traps should occur due to this T to the 5 halves gradient that occurs, for example, on the moon. But what we find is you can also predict that density of particles based on a shift, which is dependent on this parameter beta, which is a ratio of atmospheric lifetime to the orbital period of the satellite. Okay. Right, so now I think I'll move on to Io for the last half of the talk. If there are any questions on the first half, maybe that would be a good place to stop, but yeah.
Hey, Oza, if you go back to the last slide, could you talk a little bit about what those figures show? The ones you had on your summary slide?
Yeah, right. Oh yes, so I didn't mention that this was showing how the cryomagma inside Europa is coupled to its outgassing. So what this shows right here is the column density of water predicted with the cryomagma model that is venting this water outside of Europa's surface and into the exosphere. Because this detection of the first detection of plumes at Europa in 2014, or the claim by Lorenz Roth, is actually hydrogen and oxygen. So this is showing how the density of water then gets photodissociated and electron impact associated to reveal a feature such as this one below, if that makes sense.
Yeah, that makes sense. Cool.
Yeah, sorry to skip that. It's been hard to keep track of the two different bodies now. So going into IO mode, which I've been spending more of my time on. Yeah, so this is the model Dishroom that I've been naming all of the volatile evolution models after. So it's called Desorbing Interiors via Satellite Heating to Observe Outgassing model. Why satellite heating? It's because the inner workings of the model are based on tidal heating approximations at IO, and then also thermal desorption processes at Europa. So, and it's the thermal heating at Europa for ices, and then the tidal heating on rocks at IO. And so this was developed, what you're seeing here, just like a schematic diagram showing how the internal heat dissipation is calculated, then the mass loss is calculated, and then the volatile evolution d and dt is calculated. So it's a very transparent model, very easy, very analytic. There's a few integrals in there to calculate what things look like over time, but it was used to be the exact opposite of a 3D numerical simulation, in the sense that a 3D numerical simulation may have many knobs to turn, so that this particular analytic approach has much more transparency, in the sense of much less parameters, if that makes sense. With a student at the University of Bern, I was very lucky to work with Andrea Gebeck to develop a radiative transfer model, also with the idea of making it very transparent, easy. And this was, I think, at present, one of the few models that you can actually model an extrasolar torus with. And so both of these models, including Dishroom, were developed so that we can probe volatile evolution and outgassing on exoplanets and exoplanet atmospheres, and to test the idea of evaporating exomoons potentially. So extrasolar lunar volatiles. So part A and B, there's two types, in the sense that one can have a volcanic exoplanet, an outgassing exoplanet that's rocky, or you can have an outgassing exomoon that's orbiting a gas giant exoplanet. And of course, there are many other configurations that occur, but these are the two primary targets that we've been recently working on. So I call the former super IOs and the other one exo IOs, because it's more like a lunar version, a lunar-sized version of IO. And the first one, there's many close-in exoplanet examples, such as 55 Cancri E, which has caught my attention for the last couple of years, actually. This is just a little more drawn out explanation of what the models do. You can refer to that later. Yeah, so the first part of a super IO exoplanet, a rocky exoplanet. The figure on the left here shows a phase curve observation of 55 Cancri E, where at 0, this is the eclipse when the planet passes in front of the star. And then this is the secondary eclipse when the planet passes behind the star, which also blocks out light. Because you see, you're in this ramp up over here, you're seeing planet plus star. And generally, one would expect the peak to be at the subsolar or the substellar insolation point, but the peak, similar to Europa and Ganymede in terms of its O2 content, the bulk peak of this exoplanet appears to be shifted towards dusk, local time. So this is a illustration of a potential model where the surface is outgassing and it actually has a hotspot, like at Io, but unlike Io, there's not many hotspots due to volcanism. But there's a hotspot due to a thermal anomaly that is potentially evolving with the orbit. So it's orbital variability, which may be consistent. So that's one example of this effect. And so using Dishroom, one can actually model the sulfur dioxide evolution, assuming that the main constituent of this secondary atmosphere is sulfur dioxide. And so I know there's a lot of new terms here, such as magma ocean tide or a magma ocean atmosphere. But the idea of this is that these planets are so close in, and that they're inevitably in this super IO state, because even if imagine that the tidal heating is not occurring, the surface temperature or the brightness temperature in infrared by Spitzer is measured to be 2,700 degrees, at least the maximum temperature. The coldest temperature, 1,400 degrees for 55 Cancri E. So we know that there's a measured thermal gradient, and we know that at least one side should be completely molten, unless it's made of pure tungsten or something. Chondrite would certainly have a magma ocean. The other side may, of course, have condensation. And so furthermore, I wish I had more animations to show how the primordial atmosphere escapes, but work with Christophe Morticini et al. On super Earths being born from sub-Neptunes show that the timescales of keeping a primordial hydrogen-helium envelope are very short. Catastrophic for exoplanets, meaning 100 million years. So even if you produce an atmosphere, that atmosphere would escape so fast, especially for a system that's about 8 billion years old or more. So the idea that this is a secondary atmosphere, I think is pretty solid. And I think Swain et al. Found evidence of a secondary atmosphere around a different super Earth, around a red dwarf star, evidence of hydrogen cyanide, so HCN. So that's another volatile that I think has come up often in the literature. Okay, so a spectral search for exoios. So switching to exomoons now. This is the technique I've been using with our team to search for these exoios. I would say Ariel Moulet, who's in the audience, is part of this because in 2019, we published a paper based on the sodium chloride and the potassium chloride detections of Io and what we know about sodium and potassium at Io to search for sodium using the transmission spectroscopy technique. And so far, we have a very long list of exo-Io candidates, and I'd be very happy for some of these to go away so we can focus on a few systems at once and then evaluate these exo-Io candidate systems and say, hey, these systems may not actually have exomoons that have survived over the billions of years of evolution. But I think this was an important work in the sense that in 2002, there's a famous paper, Barnes and O'Brien, that said that no close-in exomoons should exist. And I think there still are several papers. So the verdict is out whether exomoons can survive migration. But the idea that a few exomoons may survive capture, for instance, or the idea we proposed in 2019 is actually not new. It's based off of a paper by Goldreich and Nicholson in 1977, which shows that the tidal Q of Jupiter and Saturn is actually anomalous. That it's 6 orders of magnitude less than it should be. And this has to do with resonant excitation in the gas giant's atmosphere due to the moon's orbital motion. So these inertial waves that are created in Jupiter's atmosphere that give it that 10 to the 6 value reported by Laney et al. This value is well known. It's a value we can use in tidal models, but we cannot necessarily use Jupiter's tidal Q on a hot Jupiter. So these close-in exomoons are obviously orbiting these hot Jupiters and hot Saturns experiencing atmospheric escape. So it's a tough problem to entangle that endogenic and exogenic problem. And of course, linking back to the tidal dissipation, the tidal Q, you can't use the same one because hot Jupiter should probably have a much higher tidal Q because the exomoons should be orbiting much closer in because the Hill spheres are much smaller. So as you can see in these in this diagram, well, it might be very small, but the satellite semi-major axis is very, very small. It's just a few, almost 2 planetary radii. So for it to survive, it would have to be hovering just very close in. So during migration, the exomoon or an exo-Io would just approach the Jupiter and then go in, but hopefully not too close and fall in. So that's a current dynamical problem at present. So very multidisciplinary, this problem, it appears to be. Hopefully not too scattered so far. But yeah, here is a, let's see, in-depth examination of these two systems. We've got 55 Cancri E on the left, outgassing on a rocky exoplanet. And then we have an exomoon, WASP 49b1. This one got a lot of press. I think probably just because of a quote about it being similar to a Star Wars exo moon. But yeah, it's both bodies, you would expect a lot of magma to be on the surfaces based on the temperatures alone. So not to overcomplicate anything, it's very obvious that these bodies would have magma and sodium and potassium potentially trapped inside these magmas. Now at Io, we know that sodium chloride and potassium chloride exists in Io's near surface atmosphere, possibly from the volcanic vents. And then we've seen outbursts of sodium clouds at Io that are linked to volcanic events, and then even extending to the plasma torus. So we'll get to that. So these are just the parameters, as you can see, and you can see how it's different for an exoplanet and exomoon. For an exoplanet, you can get much closer in, heat it up to this baking furnace, way hotter than a furnace temperature, molten temperatures of rock. And at an exo-IO, it's preferable to be farther from the star so that the star and the stellar tide does not kill the exomoon. So yeah, exactly. A stellar tide could disintegrate an exomoon very fast if it's above 2000 Kelvin, as shown by Perez, Becker, and Chang in 2013. This is a plot just to show how interesting it is to evaluate a stellar tide, because the solar tide on Mercury may affect its evolution on the location of where maybe the sodium is, causing a sodium reservoir at night that then desorbs. But the stellar tide, there's no stellar tidal heating on Mercury in the sense to give an enormous tidal dissipation. And we can see this is orders of magnitude higher than Io, sitting on this curve right here. I always think it's funny that Europa has a little more tidal dissipation than Io, but we never, at least back in the day, thought that, or had models to predict its cryovolcanism. But of course, a lot of that heat may be into its ocean, involved into creating that liquid water ocean inside. But yeah, so these are the exo-IO candidates that have this extremely high tidal dissipation that drives mass loss and then drives the volatiles that can be seen in spectroscopy. All right, yeah, so continuing on, sorry, I'm just gonna go back here. Yeah, the mass loss rates at these objects are enormous. You can see that we've got like 100 tera kilograms a second shooting out just by vaporization alone. And this is purely a temperature effect. The tides I find to be similar in magnitude due to a scaling relation that Dishoom uses to Io. But that involves knowing the rheology of this planet. We assume that the QS, the tidal Q of Io, is similar to the tidal Q of this rocky exoplanet, but it could be less, which would increase the mass loss, but it could be more. Now, for an exo-IO, these rates are also scaled to Io based on atmospheric sputtering, but also can be evaluated based on atmospheric loss from XUV radiation. And also note that the gas giant here that is hosting a putative exo-IO has a density that's half of Saturn's. So it implies this extremely inflated radius, which is another problem at exoplanets, which I think an exomoon may contribute to explaining in terms of all the extra gas, which may be opaque. Because if these exomoons are in their last 100 million years of life, then the amount of flux that you would deliver to the systems would be very large and could contribute to an actual entrainment inside the gas giant's helisphere. This is all also neglecting the magnetosphere of these gas giants. So we have a survey in the radio wavelengths where we're trying to look for these exo-IOs, and probably more fundamentally probe the exoplanet's magnetic field. I'll get to that later. So yeah, I think there's a lot of material here. So not only just going back, can you get the surface? So 0 I usually use to refer to the surface escape flux and the surface desorption. And then later you can actually get the upper atmospheric escape rate. Now this is known from the Kepler observations of the evaporation value, which shows the population of sub-Neptunes, and then super Earths, and shows that photoevaporation of XUV heating is a fair way to model the escape of close-in exoplanets. Hydrodynamic simulations seem to fare a lot better when coupled with cooling. For any modelers out there thinking of using hydrodynamic and XUV heating, it seems that H3 plus and this cooling by hydronium seems to be very important. Okay, so yeah, plasma, as I was saying, this is unknown right now at exoplanets. It would be nice to probe the exoplanet magnetic field, but we'd assume that it's Jovian-like. And then what's very exciting at a close and rocky exoplanet is all that material, just like Io, and shooting out. And why the interest of using an Io analogy is that all of the material that shoots out of Io then gets entrained into Jupiter's magnetosphere, and we can see these large sodium clouds. Jupiter's sodium exosphere extends to 1,000 Jupiter radii, for instance. And then, of course, Jupiter's plasma torus extends all the way 20 or so out to Ganymede, and then can barely hit Callisto. Well, the density falls off, of course. Yeah. Okay, what else? So Dishoom then, in terms of useful predictions, Dishoom then probes the column density, which observers can use in transmission spectroscopy, and constrain how much sulfur dioxide is inside, would be expected during transit, or how much sodium is expected during transit. I didn't talk about the Roche radius, but this is a nice tribute maybe to Chandrasekhar, whose birthday it is today. He has a nice relation in his book from 1969 that I used. But just the density of a putative rock and the density of the gas giant to the 1/3 power would give you the Roche limit for a gas giant. And so that's very interesting to consider for close-in exoplanet systems, because if you have any kind of debris nearby, one might think there might be a ring or a dusty exo ring. So that would be interesting to think about. Yeah, I'm going to fly through this so we can get to the ending. So, right, as I described, Prometheus helps us do this. All the mixture of volatile evolution and outgassing I described in the previous slides, we're trying to put that into this radiative transfer model, Prometheus, and then couple it with Dishoom, and then have this very versatile 3D radiative transfer model for future observations and also current observations. I think there's archival data that ESO has that is very, very useful. Yeah, freely available. I should have shown this earlier, but this might give a better representation, something real, something in the solar system close to home, of a beautiful image by Nick Schneider and Trauger from '95 that we readapted into our ExoIO paper, where we can see the sodium cloud here evolving and following Io, but then not following Io with all these streams. The big blob you see in is, guess who, Europa coming in, but mostly solar reflectance, although Europa has its own sodium cloud. And we can see these jets. Recommend people that are interested to check out Carl Schmitt's paper, where he he goes with a very small, modest telescope, but an amazing sodium filter. And you can catch these sodium streams and clouds and spray on both sides of Jupiter, independent of Io. And of course, if you want to follow Io, you can get more trends that way. On the bottom, this is the plasma torus, where you can see the ionized sulfur following Io as well, and of course gyrating with Jupiter's magnetic field. Yeah, so ongoing campaigns. We have one at Caltech with Catherine DeClear using Keck, and we have data that we just analyzed. I guess I can show. This is VLT convolved spectra of the sodium observations at WAS49b, which is an exo-IO candidate. I haven't done the modeling because we're still waiting the Rossiter-McLaughlin effect, which perturbs the stellar lines due to the stellar rotation, so that one has to correct for the shifts. But I saw a recent paper today that showed a 12 kilometers per second plus or minus 3 kilometers a second sodium shift, which going back to the previous frame, the atmospheric sputter sodium jet is shooting off at about 10 kilometers a second. So it's very intriguing, and I think there's a lot of room to model this stuff, especially with everyone here in the virtual room today. A lot of room in exoplanets to try to understand what is going on at these systems in terms of the plasma and the outgassing geo expertise that solar system scientists have today. And yeah, here is a simulation of sodium, which is following the optical depth. You can see that very close to the moon, and perhaps an ingress or egress, if one can actually get a big enough telescope, maybe like Keck or VLT, and expose for sufficiently long, you can start to differentiate a moon from a planet. And so this is the simulation that you would expect. Yes, of course, there would be a sodium atmosphere if it's at solar abundance at 1 part per million, but the sodium abundance at Io is like 1 part in 100. As high, it could be as high as 1 part in 10 in certain cases. So that idea, I think, is worth investigating. Yeah, so these are all the ongoing campaigns for these exo-IOs. And this top one is the latest one. It's about to be submitted tomorrow, I think, by a researcher at the Tata Institute for Fundamental Research in Bombay, where they use GMRT, which is a unique telescope if you're interested in radio, that probes the hundreds of megahertz range. So looking for the kind of decameter burst emission, but also the electron-cyclotron maser instability mechanism that most likely is fueled by, well, at Jupiter, we know it's fueled by Io, but there's also the auroral precipitation that comes from the other moons. But this isn't separate, that you can get beaming from just the circuit that occurs due to all the plasma flux, once again, that's being fueled into the magnetosphere. Yeah, so conclusion slide and then questions. But yeah, for now, I'd say the geophysical characterization, super Earth exoplanets and even exomoons is just beginning, which, as people might know, is creating a lot of space for the astronomers and geo people to interact. And volcanism coupled with atmospheric escape appears to be something that must occur for close-in exoplanets and exomoons because of the extreme tidal forces from the stellar tide, and then also the extreme UV radiation and X-ray radiation coming in, blasting these atmospheres off, meaning that if there is an atmosphere, it's likely secondary. And then, yeah, at present, several exo-IO candidates exist, and so detailed simulations and detailed observations are used to confirm or deny these claims. It would be interesting to do in the next decade. And to do that, I've actually been leading this special issue that I think Parvati very nicely advertised in the group. I know it's frontiers and not flashy Nature or Science, but it's just an open access journal where you can compile all our thoughts at present on exomoons and exorings, which are very rarely talked about in exoplanets. You'd be surprised. And we have a lot of talks about hazes and clouds and getting the radius right and things like that, but there are lots of questions to be solved. So I'm hoping that maybe we can make a nice little small ebook that can help students and anyone else to just talk about what observations are telling us at present, or what models are telling us at present, and then just think what occurs when this is at a different star system, or very close in or very far out. So yeah, with that, I would yeah, give it up to questions. And of course, leave this.
Awesome. Thanks, Oza. That was a nice and very wide-ranging talk. But yeah, very, very cool stuff. So we have around 10 minutes for questions. So if folks have questions, go ahead and either hit the raise hand reaction, or feel free to unmute yourself. What questions do folks have for Oza?
Hey, I guess I'll just ask one here real quick, because those loss rates are really high that you were calculating for these close-in exomoons. So I was wondering if you have to consider basically the erosion of the moons in addition to their ability to survive the gravitational transfer.
Yeah, that's a really good question, because it would be really exciting to start thinking about what's the initial mass of these moons. I think, yeah, as we know in our solar system, the Galilean satellites, and the biggest thing you can get is Ganymede. And it seems that Earth mass exomoons for now don't exist. But if we follow David Kipping's work, it seems that there are these giant exomoons that exist or may exist. And I know there's considerable controversy on those, but the initial mass of the moon and then eroding it seems like a fun problem to work on. But for now, I just left it at the idea that it would be following Tim Cassidy's work in 2009, where they had Earth mass exomoons and then they eroded to the current size, which roughly appears to be Io size. But different planets would have different rates, so you'd have to use different initial masses to arrive at the small size, because I think they would be small at close-in systems, or else we would have seen them. Yeah. Another thing I would say is that what if they are Enceladus sized? And in that case, I don't know if we would ever see them, because Enceladus is so small. So we may be limited into only probing these close-in exomoons by their gas signatures.
Yeah. So the other thing that I was going to say there, Oza, is that I would assume that your erosion rate for an Enceladus composition body would be terribly different, right? So when I think of when I think of something Enceladus-like in these positions of these close-in exomoons, there would be absolutely no water, right? And so you would be left with the Enceladus core, which presumably is quite a bit smaller. And so when you say an Enceladus-like body, do you mean that size, just all refractories, or do you mean what's left over after all of the water and everything's gone?
Yeah. That's why I have not pursued exoenceladi yet, because I would think it would evaporate way too fast. The water would be gone. And I think there are ideas of a lot of people working on habitability of close-in exoplanets, think of water signatures. You follow water signatures, you use Lyman alpha, it's hydrogen signatures, to try to probe how much water there was. So maybe there could be an observational hint in constraining how much water is left, or if any. for example, if you're at a system where you think the exoplanet couldn't have any water and you see a lot of water, well, maybe Enceladus, but yeah, I would think, yeah, I think based on the mass loss rates, ExoI would be better to start with, but it'd be really cool to see a simulation on Exoenceladus as well.
I got you.
Or the
Thank you. Yep.
Yeah, the evaporation of an Exoenceladus, I guess.
Okay, so question kind of related to that, but so if you were to look at it's kind of a basic question, but if you were to look at our solar system from, you know, some distance, is Io the only moon that has a chance of being detectable? Like, would any of the other planet moons be detectable at all, or do you really need something that's sort of volcanic and glowing?
Yeah, similar to, I guess, yeah, Micah's question about the disintegration rates. Just go down real quick just to show some of those rates. I think I calculated. So, well, based on the tidal heating, let's just say that the disintegration rates would probably approach Earth masses per gigayear for the closest in systems. And so that would constrain that Io size or something very small at this point. And I'm just building on that to get to the idea of would only Io be observable. I think a very large moon could be observable, which would be much larger than Io. But at present, it seems from transit spectroscopy and also transits in general, there are no like giant bodies close in transit, maybe far out from, once again, Kipping et al.'s work. But spectrally, in the technique we use in terms of identifying atomic sodium, that the volatiles we used, anything that emits that much sodium, whether it's volcanism or perhaps, like Michael was saying, the refractory elements that are left, and then that is just disintegrating. Then you could have something like an exomercury or something like that. But in terms of moons, I guess we only have Io there. And just building on that, if there are other, I guess where there's room to really work with in terms of exomoons is that there's chemistry in terms of, I just found these alkali lines because I guess surrounded by Nick Thomas and Nick Schneider always telling me how cool sodium was. But there are other lines that sophisticated models could sift through, such as, okay, maybe something like Titan, which we know has very different chemical composition, HCN, nitrogen, methane. So if you look spectrally with JWST, these other infrared molecule probing facilities, one could perhaps start building models and saying, okay, well, a gas giant emits this much HCN, but a moon should emit this much if there's a Titan there. So I think doing those kind of calculations would really start to differentiate exogenic, endogenic, and could be, yeah, many different types of moons.
Cool.
Yeah.
Do we have more questions? We have time for maybe one or two questions.
I see Tim put a comment in the chat here that the moon occults a lot of Earth light in reflected light, but observational arrangements to see it would be challenging, right? And I think that's sort of a catch here is that it is, you know, this might be happening, but how likely are you to see it? Right, because if you're at the wrong point in the orbit during the transit, you're not going to see anything, right? So if the moon was in opposition or you know between the planet and the star, you wouldn't see any of the evaporation from the exomoon, right?
Yeah, so it depends, right? Well, first of all, I'd like to say, yeah, Tim, that's a really good point because that's interesting in terms of reflection, because here, I guess we're talking about absorption. There's resonance scattering. The light from the star comes in, resonantly scatters off the ambient sodium, and then comes or we see it in the spectral signature, but reflection might also be very interesting to study in terms of shadows of the planet. And then also polarized light, some different techniques, yeah. I was just going to comment that on what Michael was saying on that, since these moons are so close to the gas giant, they have a fifth of the orbital period. So if a transit lasts 3 hours, I think you would have a 1 in 4 chance getting it in that head-on or line of sight, let's say, configuration, but then you've got 75% chance that it's still on the ends of it during the transit because it's so close, based on this slide right here, where we simulated how close this moon is, for instance. So this is the whole stellar disk, and during transit, the moon is coming along with it. But it's true that it could hide behind during eclipse. Well, it would be getting baked on one side and then being in shadow on the other, potentially, based on the orbit. But there, that could explain variability, because I still haven't gotten a good answer from exoplanet people on why they see sodium at certain systems and then they don't see it at others. So I would say that fits into the story, that more observations are needed to show maybe you're hiding a moon or you had an evaporation event. So yeah.
Yeah, you could probably see it in transiting the star, but then you've got phenomena like planets in close orbits. The moons are probably resonant in their orbits in some ways, so that makes it questionable. To see it in transit, you would be seeing, weird changes in the entry and exit phase, but then to see it spectroscopically in transit is even harder, because now it's very hard to stack the data in any meaningful way to build up signal to noise.
You mean like transmission spectroscopy to stack all the sodium? Yeah, in terms of like exoplanet and exomoon, right? Yeah, that's what we're working up against right now, because we have the data, and now I realize that I would love to just have more ingress and egress observations, but luck of the draw, while I was sitting at the telescope virtually, I was in Chile, some of our ingress observations got cut off because of clouds or windows. So it's just always so tough to get very, very large telescope time to probe every part of the phase curve that you want. Ideally, you just want to wash this thing around 20 orbits and then really stack it in different ways so that you can get the moon that's orbiting much faster than planet. Maybe use Fourier transforms to try to stack it in a different way. But for now, what I can comment on, let me see if I have I know we're out of time. I guess I can, let's see, I was just gonna escape here and go to the paper. Are you still able to see this screen?
Yep, looks good. And I know we're a couple of minutes over the hour, so folks need to drop off. Go ahead, but yeah, we can still see the screen.
Oh yeah, okay.
And
yeah,
folks,
sorry.
Stick around. Please stick around. Yeah, no, we started a little late, so don't worry about
it. Let's see. One technique. I thought I would get more Europa questions, but I'm excited that I got more Exo questions. But so yeah, I didn't show these slides at all. But one thing you'll notice here, what Andrea,
so we're still seeing the
oh yeah,
the Google slides that you were showing.
Okay, now I think yeah, sorry. So this is the MinRAS paper. This is the planet HD 1897333b, very bright star, close by. WASP 49 is very far away. It's actually tough to conclude something because there's so many, there's a couple solutions, I guess. But here, the biggest, I'd say, plus for an ExoIO solution is that the broadening of the line cannot be explained by just a hydrostatic atmosphere of a planet. And so you can try to do an escaping atmosphere. So you can see that this does work for an escaping atmosphere. It's degenerate. So then it's really differentiating between the wind of the planet. Can that wind, the atmospheric loss from the planet, supply enough sodium as a moon, or not? And we didn't show it here because he arbitrarily just pumped up the sodium from the solar abundance 1 part per million solution. But at least at WASP 49b, there's too much sodium there. So too much sodium, and then also too broad of a signal. That's number 2, because this corresponds to something like 10 to 100 kilometers a second of broadening, whereas static wouldn't have any broadening. But of course, you can have a wind escape. And then the third thing is this D2 to D1 ratio, that if it's optically thin, such as at IO, then this ratio would be much closer to 2, based on the oscillator strengths of the D2 and D1 lines. But if it's close to 1, more optically thick, as you can see from this hydrostatic atmosphere. So these are some kind of spectral tricks you can use. Nothing with the stacking though, everything is averaged in these plots, but I would really like to, in the current analysis, try to do some clever stacking. But yeah, appreciate all the questions and all the interest.
Cool. Yeah, no, this is super interesting stuff. And I did send out links to your papers on Europa O2 and sodium potassium of exomoons. So, so just reminding folks that the links to those papers are on the listserv, in case you want to go back and revisit them. But yeah, thanks for a super interesting presentation, Oza. And yeah, no, I think it's just really interesting. Like, it's incredible to me that we can think about observing exomoons. But yeah, but I think what I find really interesting about this work is just that I mean, like, you can use the modeling to try and fit both solar system observations and sort of zoom further and further out and see how far you can sort of stretch those model observation comparisons, which I think is very cool. But yeah, thanks for sharing this with us today, and thanks everyone for dialing in, and we will meet again about a month from today.
All right. Well, it's nice to see everyone here. Thanks for coming. And yeah, I'll try to join for future meetings.
All right. Take care. Bye, everyone.
Yeah.
Bye.
Micah.